here live, and thanks to the contributors of this study. So I'm going to talk about larger scale CO2 storage, let's say at a gigaton scale, and possible challenges encountering this larger scale CO2 storage, and more importantly, the potential for CO2 leakage in the next half an hour. So we are all aware of global warming and its catastrophic effects, several deadly floods, droughts, heat waves as encountered in the recent years, and the majority of them are relevant to the global warming. So different organizations have proposed several pathways to manage this challenge, to manage global warming to well below 2 degrees C, or better to say, a better scenario to less than 1.5 degrees C. And these scenarios, these pathways to decarbonize the world combine different solutions. One of them, the major one, is to make a transition in the energy supply from fossil fuels to renewables. But there are some industries, like the cement industry, the steel, or chemical ones, that are not going to be easily decarbonized. Or there are some transport means that are hard to be electrified. So, all these pathways should suggest a combination of different methods for capturing CO2 from these point sources, or if directly from the air, and injecting them deep underground where the CO2 or the carbon originally comes from. So you see here that, for example, the Intergovernmental Panel on Climate Change, IPCC, suggests more than 70 pathways to keep global warming below 1.5 degrees C, and more than 100 solutions to keep global warming below 2 degrees C. And all of them include large amounts of CO2 to be captured and stored underground at rates reaching some 10 gigatonnes per year by the half century, and even more than this value, reaching some 20 gigatonnes per year in the second half of the century. So overall, we need a cumulative storage capacity of some 1,000 gigatonnes in the subsurface to store these amounts of CO2. So the scale is quite large, and for sure we have many challenges to encounter with and to overcome. So, apart from the capturing point, that is the efficiency of capturing CO2, and apart from the economical points, there are several challenges in the storage part. One of them is the available resources. So we have to store hundreds of gigatons of CO2 underground in the upcoming decades, and there's a challenge if there is available resources underground or not. It's quite uncertain, but estimates shows that it could be as large as 10,000 gigatons, the available resources for storing CO2. But anyway, injecting such large amounts of CO2 means injecting worldwide at basin scale. So you see here the distribution of sedimentary basins in the United States, and the arrays of wellbores in each basin that should inject simultaneously to handle and reach the set targets. So, a dense array of wellbores will inject basin-wide simultaneously, and it gives rise to large overpressures. So simulations show that it can be as large as 10 MPa. So if there is high connectivity between the storage targets and the underlying basement, the crystalline basement, where it's usually critically stressed and the faults are more prone to seismicity, then induced seismicity could be a challenge. But the more important one is the potential for CO2 leakage through the media, through the rock layers, back to the surface. If CO2 reaches a shallow aquifer, producing potable water, then some chemical reactions may be triggered, some heavy metals may be released, and the quality of water may be degraded. But if CO2 reaches the surface, it can be harmful to vegetation, to people, and to animals. So, for example, we are giving an example from the Mammoth Mountains in the US, where CO2 reached the surface. The source of CO2 was volcanic reactions at the depth of 3,000 meters, and the released CO2 found its way to the surface from some faults. And as you see on the right side in this image, it dried some trees there. And also some people exposed to CO2 there, some visitors, also hospitalized due to lung exposure to CO2. As you know, some 30% CO2 concentration in the atmosphere can cause death. So it's a critical challenge to be addressed that CO2 remains safe underground, and at least for 10,000 years, it will not leak at the surface, because the effectiveness of CCS is based on at least storing CO2 deep underground for 10,000 years, based on some evaluations. Okay, so several studies have been performed. These studies require performing numerical simulations of CO2 flow and transport. So the scale is very large, it's basin scale. We have different layers from target formation deep underground to surface. So we have a large spatial scale. We have to measure it both numerically and discretize it both numerically and both temporally and spatially. So the computational cost is very large. And the existing studies, therefore, has been limited to some decadal or century periods. But we are going here to extend the duration of the evaluations to the geological time scale, it's million years, through an approach that I'm going to start. So let's back to the problem of gigaton scale or basin scale CO2 injection. So we have a dense array of wellbores injected simultaneously. Here I show a 4x4 cluster. And so the wellbores are separated, are distanced from each other 10 kilometers. So they're densely located in the basin, and they're injecting simultaneously in the same target aquifer, or maybe in different horizons at different depth. But what happens is that we have kind of symmetry in the problem, in the XY plane shown here. And if we suppose that the problem is homogeneous, the rock properties are homogeneous there, we can say that we have some plumes that are going in the same way from each wellbore, but the no flow boundary between the sides. So I've simulated this problem. So you see the target aquifer in the middle, caprock above that, and base rock below that. I injected for 30 years at a rate of 1 megaton per year. The no flow boundary is on the right side. So you see that the injected CO2 forms a plume, and due to lower density compared to the resident brine, it floats over the resident brine and preferentially propagate laterally at the top boundary of the formation. But as the injection stops, the plume is also still going to propagate laterally, but also to reshape vertically due to buoyancy. So I would say, at least our simulations show that the lateral the lateral propagation of the CO2 plume in the reservoir in the post-injection period will be slowed down significantly compared to the injection period. And it tends more to reshape vertically due to buoyancy. And these observations, these simulations are in agreement with demonstration projects in Ketzing, Germany, or in Bothwell in Australia, where the velocity of CO2 plume propagation in the reservoir has decreased significantly compared to the injection period, according to the geophysical observation in the post-injection period. So still CO2 in the post-injection period can propagate for some tens of meters, hundreds of meters in the long term, let's say a decadal or century time space, but these periods are negligible compared to our geological time scales of interest to our problem. So we can say that we can neglect the lateral distribution, the lateral propagation in the post-injection period, and assume that a 1D model can capture the dynamics of CO2 migration in the post-injection period in the long term. So here you see a geological setting and a plume at the end of injection that became somehow stationary in shape. And we are going to pick a slice of the model, a 1D model, as simulated in the long term, and see how CO2 will evolve, will migrate with time. I would say that our model will draw an upper bound limit to the potential for leakage, because some mechanisms, some trapping mechanisms like residual trapping or mineral trapping are not going to be accurate in our simulations. Just two-phase flow of CO2 and brine without hysteresis and dissolution of CO2 in brine is accurate. So we have two-phase flow of CO2 and brine and CO2 migration by molecular diffusion. Different geological settings can be considered, but I here present two general cases. The first one on the left is a high-frequency alternations of aquifers and caprocks from the target reservoir here at the bottom to the surface. And the other case is the case that you have a thick but single caprock overlying the injection horizon. Again, I consider two cases for the single caprock, a caprock relatively with higher thickness, with a thickness of 550 meters, and the other with a thickness of 250 meters. So the former, the multi-layer system, is representative of the Illinois Basin in the US, where two CO2 injection projects have been performed. The Decatur project, the demonstration project, that injected 1 megaton during 3 years, and an industrial level CO2 injection that injected some megatons, but with a target of injecting 5 megatons per year in the near future. And the later one, the single caprock, can be representative of the Insala CO2 storage project in Nigeria. So our approach, like any other one, has two steps, but we are going to, but they are going to be more important here. The first one is assigning the material properties, and the other one is initialization of the model in a way that well represents the CO2 plume in the post-injection period. So I assume that we only have two materials, an aquifer and caprock. So all aquifers have the same properties, all caprocks have the same properties in our geological setting. The aquifer is highly porous, highly permeable, with values, with properties from the bare sandstone that characterized. And the caprock should be of low permeability and high capillary interior pressure to seal the CO2 in the reservoir and prevent its leakage. So good candidates can be high clay shales. Okay, but there are multiple evidences that showing that shales properties, shale transport properties, are very scale dependent. So you see here on the top right, a compilation of shale properties, shale and clay properties. Those data in the background, the lighter points are data from the laboratory measurements on intact shales in centimeter scale samples, and the other ones, the darker ones, are data from field observations or well-test data. So you see that the permeability of field data or the permeability of shales in field scale, regional scale, are up to 3 or 4 orders of magnitude larger than those from the laboratory measurements. And there are also evidence from CO2 injection, for example, in the Sleipner project in Norway, that the capillary interior pressure may be much smaller than megapascal values obtained from the laboratory measurements. For example, here in the Sleipner, CO2 was injected in the Otzer Formation sandstone, and there were a regional shade seal above that, but also some intra-formational shale layers in the Otzer Formation. After injection, they found that some CO2 accumulations were occurred below these intra-formational shale layers. Some thin layers of shales with thickness as low as 2 or 3 meters. So they have reproduced these accumulations by invasion percolation methods and found that the intercapillary pressure of these intraformational shales are as low as 50 kilopascals, so much smaller than those from the laboratory measurements, which are as high as 10 MPa. Okay, so to deal with the effect of such scale-dependent properties, we consider 2 cases, caprocks with properties representative of intact shales measured in the laboratory. So here we use the values we have measured on Ocarina clay with high clay content. So the permeability is in the non-Larsen range, the capillary pressure is 2.5 MPa, and the relative permeability to CO2 are governed by power laws with exponent as high as 6. And we have a caprock named degraded, that is representative of a highly fractured, pervasively fractured caprock, just like that in the case of Sleipner, with permeabilities 4 orders of magnitude larger and interpressure as low as 100 kilopascals and relative permeability exponents of 3, just the same as that used for aquifers. That allows for further mobilization of CO2 and brine in the caprock. Okay, so the next step is initializing the model. So we have to initialize the model in a way that at the end of injection, at the end of 30 years of injection, we have a CO2 plume or a CO2 pressure representative of the axisymmetric models that I've shown in the previous slide, representative of the real case of CO2 plume in the reservoir at some years after shutting in the wellbores, where the CO2 plume becomes stationary in shape in the reservoir. So I inject at 2 lateral sections on the upper part of the reservoir, while I allow for some brine leakage at the bottom of the reservoir. So we do not expose no flow boundary conditions here, because then this results in large overpressures, not realistic overpressures. And we do not allow for constant pressure here, because then CO2 injection displaces all water and the reservoir becomes fully saturated with CO2. Again, that's not would be realistic. So we allow for some CO2 leakage, for some brine leakage by adjusting this parameter, this gamma multiplier, that adjusts the pressure versus the flux at this boundary. So we calibrate this parameter to reproduce real field conditions in the post-injection period. So let's see what happens. First, starting with the case of multi-layered system, and the case that the caprock is of intact shale properties. So you see here on the right that upon injection, you're going to create a CO2 plume, and the CO2 will not enter into the caprock overlying the reservoir, merely because the interpressure is high, so it's not going to penetrate into the caprock. So you see here, I consider a point at the interface between the reservoir and the base of the caprock, and you see that upon injection, we are going to have some CO2 invasion into the base of the caprock, but it will be limited to some centimeters at the base of the caprock, because the capillary pressure induced at the caprock is not enough to desaturate to overcome the high interpressure of the caprock. And you see here from the relative permeability curves that the saturation lies, the maximum saturation at the base of the caprock lies in the range from 8 to 1, where CO2 is almost immobile. So in the post-injection period, again, we do not see any CO2 invasion into the caprock by buoyancy, but instead CO2 dissolves in water, so it diffuses upward and downward, overlaying and underlying formations. And due to this dissolution, the pressure in the reservoir decreases, so we can expect that the capillary pressure decreases as well. So the saturation, the brine saturation is retrieved in the post-injection period as brine imbibes back into the pores and blocks all the pores, and the initial state of full saturation with water is gained. So we see here distribution of CO2 mass with time in the reservoir. After 30 years of injection, we have a large amount of CO2 in free phase in the reservoir, some CO2 dissolved in water present in here. Target aquifer and some CO2 dissolved diffused into the overlying formation, into the caprock. But with time, the contribution of the free phase CO2 in the reservoir decreases, while the contribution of dissolved CO2 in overlying layers, in underlying layers increases. So I would say that after 1 million years of running the simulation, the CO2 by molecular diffusion penetrates only 200 meters across the geological medium. So it will be indefinitely safe. In this case, CO2 will remain for geological time and space in the subsurface, as molecular diffusion, as you know, is intrinsically a slow process of dissolved species. Okay, let's proceed with the case of degraded caprocks. Again, multi-layered system with degraded caprocks with low interpressure and high intrinsic permeability. So what happens is that during the injection, CO2 will penetrate the caprock, break through the caprock, displaces the water in the overlying aquifer and the secondary aquifer, and also penetrating the secondary caprock. So I will explain the problem in the same way as the previous one, with a point at the base of the primary caprock and a score point at the base of the secondary caprock. So upon injection, the capillary pressure is enough to desaturate the base of the caprock, and the same observation can be made for the secondary caprock, but with some delays, the CO2 pass through the caprock and aquifer and reach the secondary one. And at the maximum desaturation state, we see a relative permeability of more than 0.6 to CO2. CO2 is quite mobile and can flow through the medium. In the post-injection period, CO2 continues to flow through the secondary caprock. Again, it passed through this one, the secondary one, but cannot go further from the top of the third aquifer and penetrate the third caprock. Why? Because the pressure profile is continuous. So we have the same pressure in this point on the top of the aquifer and the point at the base of the caprock. And irrespective of the capillary or other transport properties of the aquifer of the caprock, but the saturation is dependent to their properties. So for CO2 to desaturate and penetrate the third caprock, it needs high pressure, a high overpressure to overcome the capillary interpressure of the caprock. But at this pressure, as pressure profile is continuous, we can expect large desaturation in the caprock. What happens to this desaturated water, to this mobile water? It has to be penetrated into the caprock, into the overlying caprock. But this caprock is of low permeability. So it prevents you to it prevents brine leakage into the caprock. So we need a high CO2 pressure to push brine and desaturate this aquifer so that after that it can penetrate the caprock, the overlying caprock. This would not happen at that point. So we are not going to experience a further CO2 rise from this point on. And again, CO2 transport becomes diffusion dominated. So as CO2 dissolves in water, again the pressure decreases, the capillary pressure decreases, so the water saturation both in the overlying caprock and the primary caprock right above the target formation increases and finally recovers its initial value. Okay, so in this case, with the same plots as of the previous one, after 30 years of injection, we have some CO2 in free phase in the target formation and also some CO2, some large amounts of CO2 in free phase in the secondary aquifer, in the aquifer overlying the other one. Some CO2 dissolved in water in the overlying caprock and layers, and some in the underlying. But as time goes, the amount of CO2 in free phase decreases and the contribution of dissolved CO2 increases. So again, CO2 transport becomes diffusion dominated and can only penetrate for some 330 meters, so some 100 meters extended compared to the case of intact shape. So I would say that even if the caprock is of low quality, is of degraded shape properties, I can say that again, CO2 cannot rise that much. And again, it would be a safe option for CO2 storage. But what happens if you have a single caprock compared to the multi-layer system? If the caprock is of high quality, is of intact shape properties, the results would be almost the same as the previous ones. No leakage would happen, the system would be completely diffusion dominated and safe. So I only present here the case of single caprocks with degraded shape properties. Okay, so you see here on the top, the case of thick caprock with a thickness of 550 meters. Upon injection, during the injection, CO2 penetrates into the caprock and penetrates for some 110 meters into this caprock. So compared to the case of multi-layer system, that CO2 could rise for some 60 meters, it's quite large. It's kind of double compared to the multi-layer system. And the reason is that there is no aquifer, no low capillary aquifer in between to induce that effect that I've explained, the effect of continuity of the pressure profile, but discontinuous saturation profiles. So CO2 can rise much larger into the caprock compared to the multi-layer system. The same observation is made for the thin caprock with a thickness of 250 meters, but as you see, at the end of injection, CO2 could rise for some 200 meters, again much larger than the case of thick caprock. What's the reason? I can explain it by recalling that CO2 flow, in fact flow is not a local process. And the properties of overlying formations are going to affect CO2 penetration here at the bottom of the caprock. How CO2 penetrates the caprock, so it push the brine in the pore network out of the system, and I can say that brine advances in the caprock much in advance of the CO2 because the relative permeability to brine is almost equal to 1 as the median is initially saturated with water. So I can explain further here with the pressure versus depth profile. So this is the storage formation. We have a caprock, thin or thick, and we have an overlying aquifer. The aquifer is of high permeability, so it retains the hydrostatic pressure in the media. Suppose that we have a constant pressure here at the top of the storage formation. So I can say that for the case of thin caprock, the pressure gradient that derives flow is larger than the case of thick caprock. Or equivalently, if I initiate a flow, a constant flow, a similar flow for the case of thin or thick caprock, a smaller overpressure is required to generate this flow, this flux. So I would say that in the case of thin caprock, CO2 can much more easily displace water out of the pore network, so it can penetrate much deeper into the caprock. Now let's see what happens in the post-injection period. In both cases, it's just a matter of time, but in both cases, CO2 will finally pass through the caprocks and appear in free phase at the top of the caprocks. It takes it's in the order of decades, 1 century to happen for the case of thin caprock, and it takes in the order of 1,000 years to appear as free phase on the top of the caprock. This CO2 is here in free phase. It rises by buoyancy, but at the same time, it's going to be dissolved in water. So there will be competition between buoyancy rise and CO2 dissolution. And the buoyant rise of CO2 will depend on the budget, on the CO2 budget available here at the top of the caprocks for its rise. At some point, the buoyant CO2 cannot rise anymore into the aquifers because the whole CO2 is going to be dissolved in water, and the process becomes again diffusion dominated after some 1,000 years. But it's quite enough to deliver CO2 here at the top of the caprock to the surface for the case of thin caprock. So this is the concept of migration-assisted trapping of CO2. So the migration-assisted trapping of our model is just dissolution, but it can be assisted by residual trapping. The concept is going to be tested in a pilot test in Australia, and CO2 will be injected in a thick aquifer at a depth of 3,000 meters. There's no regional caprock there, only some thin interformational shale layers at shallow depth. So the injected CO2 has some 2,000 or more meters to rise along the media, so enough space for being dissolved or trapped by residual track. But anyway, without any regional seal, without any structural seal, such kind of trapping are not going to be to store more than a few megatons per year. So in summary, I would say that for gigaton scale CO2 storage, a regional structural sealing, a regional caprock is required. If the settings are a sequence of shaded caprocks and aquifers, even if the cumulative thickness of the caprocks are much smaller than an equivalent single caprock, and even if the caprocks are pervasively fractured, so there are degraded shade qualities, I would say that CO2 will indefinitely remain safe underground or geological time space. But if they have to inject in a setting that only a single caprock present, to unlock maybe more resources, more capacities for injecting CO2, then high resolution monitoring is required both during and after injecting CO2 to ensure that CO2 will remain deep underground. Thank you, and I'll be happy to answer your questions.
Okay, thank you very much. I don't know whether, let me see the, maybe there are people online or on the website to say if you want to ask a question. Jesus wants to ask a question. Go ahead.
Yes, I have several questions actually. Well, first of all, congratulations, Iman. It was a very nice, very clear presentation. Even though I did not hear you well, I could follow very well the presentation. So yes, congratulations, because it was a very nicely organized presentation. And also the message is clear, and overall I think it is right. However, there are several things I do not quite share with you. The first and perhaps most important is when you talk about scale effects in caprocks, and caprocks do have very severe scale effects. Can you put that slide where you were showing the properties of good shale and bad shale and entry pressures and everything? You spent quite some time in that slide. In that slide, you were showing that the permeability of fractured shale can be 4 orders of magnitude larger than the healthy shale, which my reading of that actually, yeah, is 10 to the minus 20 versus 10 to the minus 16, huh? The permeability.
Yeah.
And this is a concept that now Seal and others, including myself, yeah, for groundwater flow is okay. That concept works. But I argue that for multi-phase flow it does not work, because the effective equation for a fractured shale cannot be the same as the equation you have for homogeneous shale, simply increasing the permeability and reducing the entry pressure, which are the 2 most important parameters here. Huh? So my point is, I don't agree with the physics you're using. My point is you would have to use an upscaled equation, which would be different from the multi-phase flow for a homogeneous medium. Am I explaining myself? Do you understand my question?
Yes.
Yeah.
Yeah, sure. I agree with you. But our case here, as I said, really, if I insist on the case of pervasively fractured shale, I mean that there are multiple, very closely spaced fractures, tiny fractures, not large fractures.
Iman, I don't hear you very well. So please speak slowly and vocalize very well.
Yeah, so I'm closer to the microphone. Can you hear me better?
No, I hear you, but the sound is not very good.
Okay, so I insist that our case here, when I say in the largest scale, we have a shale with a higher permeability, I mean a pervasively fractured shale, not in fact, the case that fractures are very tiny, are very close to each other in the shale, so they are not apart from each other, they are not localized, so they are not going to lead to localized flow. But instead, we can say that in an REV, we can assume that we have enough fractures, so we can say that the Darcy flow can be applied in an REV with homogenized, higher permeability in each cell. But if we have large fractures, very spaced fractures in the shale, then it would be localized flow, and for sure this approach cannot address, in fact, the flow and migration of CO2 in a reliable way.
No, but the point is, when you see, I have never seen 4 orders of magnitude, but I have seen 3 orders of magnitude difference between local permeability values and large-scale effective permeabilities for water flow. Now, the point is, this is what you see. You see that the effective permeability at large scale is much larger, 3 or 4 orders of magnitude larger than the permeability you derive from small-scale tests.
Yeah.
Not even core tests. I mean hydraulic tests, but small-scale hydraulic tests.
Yeah.
And this is all you see. You do not know if it is due to a bunch of small fractures or if it is due to large concentration of fracture zones, if it is due to faults, poorly sealed faults, or you don't really know. And I explore this topic in detail in granite. In granite, when we were working on nuclear waste disposal, we did analyze that in detail. And our conclusion was that you have a whole suite of fractures. In fact, the people who specialize on characterization of these fractures, they concluded it's a fractal distribution of fractures. So my point is, you do not know if your model is correct.
Yeah, you're right. But for sure, if the permeability is localized, if you have discrete fractures, if you have faults, then there will be the probability of CO2 leakage. There are many evidence that showing CO2 leakage through faults is not possible to happen. In fact, the possibility is low because of geochemical processes, because of the multi-layer system, the heterogeneity between the high permeability and low permeability layers. But still, the possibility of leakage would be only through such localized fractures. And we wanted to show here in this study that if there is no such localized flow, we would be indefinitely say that CO2 leakage would be impossible. And CO2 will indefinitely remain safe in the underground for geological timescales.
No. That definitely I do not buy. And you think about your response, huh? Because up until now I agreed with everything. I mean, there is this little disagreement on the effective equations, but what you say I definitely disagree with. You do not know. And you do. Why do you say it is physically impossible for the CO2 to flow through if you have a open path? Of course it not only can, it will flow, for sure. I mean, we have this model that in shales, faults tend to be filled with clay, so permeability is low, blah, blah, blah. Yeah, this is the model. But if this is the case, then you would not have an effective permeability which is 4 orders of magnitude larger than the small scale permeability. And to me, this is very concerning because there is a disagreement between the conceptual model and the observed data. So even though I tend to agree with the model that the multi-layer system is safer, and I like, as I said, I like your presentation, I don't think you can be sure. I mean, imagine there is a tube, a pipe connecting the two, and a pipe on an area of 1,000 square kilometers would imply, yes, perhaps a few orders of magnitude increase in the effective permeability. You do not know if what you have is a pipe, if what you have is a discontinuity filled with sand. And we know enough geology to know that sedimentary processes sometimes are kind of unpredictable. I mean, you do not know beforehand.
Well, thank you first for your presentation.
I think you should go.
Right here.
Okay.
Notes at home. Focus.
Okay, go ahead.
So thank you first of all, interesting talk. I just wanted to ask you a simple question. Why is this 30 years injection period so recurrent in your analysis? Is it something that current injection plants are considering, like a time span for actual injections? Would you explain a little?
Yeah, it's common practice. In fact, we usually run the simulations for 30 years or 50 years. In fact, it would be common practice in the near future. if you want to reach the gigaton scale CO2 storage, then these basin-scale injections, extended over time, so decadal injections become future. Yeah. But for sure, it will depend also on the capacity of the reservoir, on the overpressures that we are going to create by injection, then the possibility of induced seismicity. So many parameters will be important. But 3 gates of injection.
Okay. You expect in actual practical settings to be the injection period to be longer?
Yeah, it can be, but I said it depends on the characteristic of the reservoir, on the thickness of the reservoir, its distance from the crystalline basement for sure, on the layers between them, if they can seal CO2, if they can seal overpressure migration downward to the crystalline basement, and the quality of the caprocks, their thickness, but for sure, fact, the CCS industry would grow in the upcoming decades and become even larger than the petroleum industry, the current petroleum industry.
And one last question: in your simulations, when you consider the wells, the boreholes, were these fully penetrating the aquifer or only a partial penetration? Could you?
No, in the case I presented here, it's the case from the Illinois Basin.
Mm-hmm.
So this Mount Simon Reservoir, and this is not the caprock. In fact, it's it's upper layers. In fact, the Mount Simon layer has 5 sections. We inject here in the full thickness of the bottom 2 sections. We have 3 other sections on the top. The permeabilities are 3 orders of magnitude smaller, 10 to the minus 12 here, 10 to the minus 15 here. So as you see, even these are not shales, but some 3 orders of magnitude less permeable than the target formation, and they can retain CO2 in the reservoir.
Okay, and CO2 is entering through the whole lower layer, let's say.
Through the whole thickness of the on the 2 lower layers, and it's axisymmetric model with no flow boundaries on the right side. The dimension is 10 kilometers on the 10 kilometers in the radius.
Okay, thank you.
Okay, actually, I would like to ask also a question. I mean, here so that very often when you have these type of plumes, of course, here you have a high salinity, so it's heavier, it's denser,
Yeah.
and then of course you have all these type of fingerings,
Yeah.
which are difficult to simulate,
Yeah.
and especially in your 1D model. But first, you take that's the difference into account, you know, when CO2 is injected. When it's dissolved in water, the water becomes more dense. No?
Yeah.
But how would this affect, let's say, your 1D simulations? Because of course there's more dissolution of CO2 than you calculate.
Yeah.
I guess.
Yeah, you're right. For sure, there are some instabilities in the post-injection period and at the lower period of the CO2 plume. So there will be some dissolution, some fingering of the dissolved CO2 downward that further helps CO2 containment in the underground. So we are generally 4 trapping mechanisms: structural trapping, dissolution trapping, residual trapping, and chemical trapping. So we just consider dissolution without fingering, as I mentioned, that can play a role, and structural trapping. So no residual trapping, no chemical reactions and mineralization, so CO2 storage by mineralization. So we say that neglecting them will help us draw an upper boundary. So our model is very simple. We are not considering many other parameters, but I think that these parameters, neglecting them, in fact, would put our estimates on the safe side. But for sure, we can That can be addressed as well.
Yeah. Okay. Would have a little more comments or
I think Khasif has some questions.
do you have more questions, Jesus? Your microphone is off.
It's okay.
It's okay.
Thank you.
Okay, if there are no more comments or questions, then I think we can end this seminar. Thank you very much for your
Thank you.
and thank you for the audience. Okay.